So in chapter 4.4, we're going to look at properties of logarithmic functions. Our objectives in this chapter is apply the product, quotient, and power properties of logarithms. We're going to write logarithmic expressions in an expanded form, and we're going to write logarithmic expressions as a single logarithm. And we're going to apply the change of base formula. So our first objective is to apply the product, quotient, and power properties of logarithms. Let b, x, and y be positive real numbers where b does not equal 1. The product property is the log b of x, y equals the log of b, x plus the log b, y. The quotient property, log b of x over y, is equal to the log b of x minus the log b of y. Finally, the power property, log b of x raised to the p power, is equal to p times log b of x. So now we're going to assume for our next numbers and for our problems in this chapter that all variable expressions represent positive real numbers. So in examples 1 through 3, we're going to use the product property of logarithms to write the logarithm as a sum, then simplify if possible. So for example, in number 1, we're going to use the property of log summation. So here we have log 2 plus the log x plus log y. So for problem 2, we have the log 2 of 2 plus log x plus log y. Now we can simplify this. The log 2 of 2 is just 1 plus the log of x plus log of y. In our last one, we just have the natural log of 3 plus the natural log of a plus b. Notice here we do not distribute the 3 inside the parentheses. It doesn't make any sense. So in this case we just have the natural log of 3 plus the natural log of a plus b. In examples 4 through 6, we're going to use the quotient property of logarithms to write the logarithm as a difference. Then we're going to simplify if possible. So for number 4, we have the log 7 of z minus the log 7 of 49. But this can be simplified to be the log 7 of z minus the log of 2. Actually, it's not even the log of 2. It's just 2. Does everybody see why? So number 5, we have the log 5 of, or log of 7, I'm sorry, the log of 7 of a minus the log of 14. You could leave it like this. We could, in some sense, change 14 to 7 times 2. So we could get the log of a minus the log of 7 times 7 times 2. And then we can see this is going to be the log of 7 minus log 7 of 2. So this is now just the log of a minus 1 minus log 7 of 2. So that's a little bit more complicated, but there gives you an idea of where we're heading to a lot of this. This last one is just equal to the log of 100 minus log of x plus y, and you can see that this is just 2 minus log x plus y. So there we go. Now we're going to apply the power property of logarithms. In this particular case, we start out with number 7, and we see that this is just 5 natural log of x. For number 8, it's just 5 log e, which is just equal to 5. And in the last problem, we're going to rewrite this as the log of x to the 2/3, which is just equal to 2/3 log x. There we have it. Our next objective is to write logarithmic expressions in expanded form. So in our first example, we have the use of the product rule and of the quotient rule. So we're going to show you how this is done. So here we have the log 3 of 5z minus the log 3 of w. Notice that in this case I'm just dealing with the quotient rule first, and now I'm going to apply the product rule next. So here I have the log 3 of 5 plus log 3 of z minus log 3 of w. Now we're going to see problem number 11, and here again what we're going to do is we're going to break this first up into just the quotient rule first. So I'm going to do log 7 of AC minus the log 7 of 5d. That's the first step. And now I'm going to apply the product rule. So I'm going to get the log 7 of A plus log 7 of C minus log 7 of 5 minus log 7 of D. Sometimes I will write log as LG and distinguish between LG and LN. It's just a simpler way of just writing it. So now we're going to expand the sums or differences of logarithms. In number 12, we're going to apply both the power rule and the product rule. So the first step is actually to apply the product rule first, and then we'll apply the power rule. So in this particular case, we're going to apply ln x squared plus ln of y. And now we'll apply the power rule, which is 2 log of x plus the natural log of y, obviously. And there we have that particular problem done. In number 13, we're going to rewrite the logarithm as in powers first, since we have it in a radical. Then we're going to apply the quotient rule, and then we're going to apply the power rule. So here's what we're going to do. We're going to rewrite this as ln times x to the 2/3 divided by w plus z. That's the first step. Now I'm going to break this up by the quotient rule. So I'll have ln times x to the 2/3 minus ln w plus z. Now I will use the power rule. 2/3 ln of x minus ln of w plus z. And that's the final result. So here things are slightly a little bit more complicated. We're going to rewrite the radical symbol into powers of the logarithm. So we're going to rewrite this essentially in the following way. So this is the log 2. And we're going to apply the square root symbol. Now, when we do the square root of 4, we're going to get 2x to the 1/2 power divided by y to the 1/2 power times z to the 3/2 power. So now we have everything in the power situation. The next step is to use the quotient rule. So now I have the logarithm of 2x to the 1/2 minus the natural log, obviously, of y to the 1/2 z to the 3/2. Now I can use the product rule. In this case, now I'm going to get the log of 2 plus the log of x to the 1/2 minus, now I'm going to do a bracket here, so I'm going to get the log of y to the 1/2 plus the log of z to the 2/3, or the 3/2. Now, I should have had a bracket there, I'm sorry. So now I can apply the power rule. So I'm going to leave this as log 2, or natural log 2, plus 1/2 log x, natural log x, minus 1/2 log y. Now I've got to apply the negative through. I'm distributing the negative, but I'm also going to use the power rule here. So I have 3/2 log z. There we go. There's the final expansion of this particular logarithm. So here we also have a more complicated expression, but we can also break this down into pieces. So we're going to rewrite this logarithm based on base 8, right? So I'm going to rewrite this as 8 squared x squared y divided by 3zw raised to the third power. Now I can do log 8 of 8 squared x squared y minus log 8 of 3zw cubed. Okay, so I applied the quotient rule after I rewrote it. Now I'm going to apply the product rule, and so when I do the expansion it's going to get a little messier. So now I have log 8 of 8 squared, and we're going to know what that is in just a second, plus the log 8 of x squared plus the log 8 of y minus, and here we're going to do a bracket again, log 8 of 3 plus log 8 of z plus log w cubed. And now we can start combining terms or looking at powers. In this case, this just becomes 2. So I have 2 plus 2 log 8 of x plus log y. Now I'm going to distribute the negative. Log 8 of 3 minus log 8 of z plus 3 log of w. There it is. Our next objective is to write logarithmic expressions as a single logarithm. So now we're going to combine logarithms. So in this case, we see that we're going to apply the quotient rule in reverse. So this is just going to be the log of 4x minus 3 divided by x. And in number 17, we're going to do the same thing, except we're going to take one more step before we actually do the product rule in reverse. So what we're going to do is we're going to do log 2 of z plus log 2 of y to the fourth. So we used, in this case, we did the product rule first, the power rule first, and now we're going to use the product rule. So now this is log 2 of z y to the fourth. There it is. So now we're again going to write the logarithmic expression as a single logarithm with a coefficient of 1 and simplify as much as possible. So in this particular case, I'm going to rewrite some of this by using the power rule first. So here I have the natural log of x cubed plus the natural log of x minus 2 minus log 5. And now I see I can use the product and the quotient rule. So now I'm going to have x cubed times x minus 2 divided by 5. So all this is part of the same logarithm. Okay? The next one is a little bit more challenging. The first step, again, is to use the power rule. So we usually, when we're expanding logarithms, the power rule is usually done at the end. And we do either the quotient rule or the product rule first. When we get to the stage where we're simplifying or we're putting it into a single logarithm, we typically do the power rule first, and then we end up doing the product and the quotient rule after. So in this case, that's exactly what we're going to do. So we have a 2 outside the logarithm x plus 1, so we're going to distribute the 2. So here we're going to have 2 log x minus 2 log x squared plus, now I'm going to distribute the power rule right away, so this is going to be the log of z to the 9th raised to the 2/3, we're going to have to deal with that, minus the log of z. So I've kind of used some of the power rule, but I've got one more thing of the power rule that I got to do, and that is I've got to do log x squared minus the log of x to the 4th plus the log. Now I'm going to, the 2/3 goes away, and I have z to the 6th power minus log z. Now you can see what happens. We have the log of x squared over x to the 4th, and then we have plus the log z to the 6th over z, and this is going to be equal to the log of z to the 5th over x squared. Do you see why? Because when we multiply these two together, they're going to combine, right? But we can cancel the x squared and the x to the 4th to x squared, so it would be 1 over x squared times z to the 5th, because we take a z out of both of these. Okay, that's that particular one. That's a little bit more complicated, but it was very interesting. So here we also have a more complicated scenario. In this particular case, I have a -2 here that I'm going to be dealing with, and so I'm going to do the power rule kind of first. So I have log 5 of x plus 5 raised to the -2 power plus log 5 of x, and then I'm going to rewrite this as log 5 of x plus 5 times x minus 5, because it's a difference of squares. Now, I'm just going to use the product rule here, right? So if I use the product rule, I get the log 5, and on top I'm going to get x, and I'm going to get x minus 5 times x plus 5, and on the bottom, because I have x plus 5 raised to the -2 power, I have x plus 5 squared. And we can see that I can simplify this because the square goes away of one of the x plus 5's. So now I'm going to get log 5 of x times x minus 5 all over x plus 5. So that's our final result. So in the next three examples, we're going to use estimations of a logarithm. Log b of 2 is equal to 0.437. Log b of 3 is equal to 0.6826, and log b of 7 is equal to 1.291. And now we're just going to estimate these logs based upon those three numbers. And what you can do is do the following. So I can rewrite log b as 7 times 3, which is equal to the log b of 7 plus log 3 of 3. B of 3, I'm sorry. I was about to say that's just 1. So all I do is I just plug the numbers in. It's just 1.2091 plus 0.6826. And you say, well, why are we doing this? And it turns out in the old days when we were doing tables, this was one way to find out logarithms, one particular way. And when you're going into trigonometry, there's also ways of looking at sines and cosines of different angles, and you can do the same kind of idea. It's not exactly the same, but it has the same feel for it. In this particular case, when I add the two together, I get 1.8917. So for 22, I have the log b of 3 squared, which is equal to 2 log b of 3. And so this is just equal to 2 times 0.6826, and when we did the calculations, we get 1.3652. And then finally, again, this is just a difference. This is log b of 7 minus log b of 2. And you can see that this is just 1.2091 minus 0.4307. And this one is just equal to 0.7784. So now we're going to apply the change of base formula, and we're going to show you that next. So typically we let a and b positive real numbers such that a doesn't equal 1 and b doesn't equal 1. Then for any positive real number x, the log of b of x is equal to the common log or any kind of log of a of x divided by the log of a of b. In other words, in order to find a different base of a number, we can just apply either the common log. So for example, if we have the log of 3 of x, we could just apply the common log of x divided by the common log of 3, and or we could do the natural log of x over the natural log of 3. So this gives us the ability to find any log of any base. So now we can apply this particular issue. We can use the natural log, or we can use the actual common log. I'm going to use the common log. So if I want to find what this is actually numerically is, I can change this to be the log of 15, that's a base 10, divided by the log of 7. And that equals 1.3917. That's rounded to 4 decimal places. Now we're going to do the same thing for number 25. We're just going to use the common log again of base 10, and we'll use our calculator. So this is the log of 0.3 divided by the log of 5, and that equals a negative 0.7481 raised, that's to 4 decimal places. Well, that concludes our chapter on 4.4 on rules of logarithms and how do we expand or apply logarithmic rules and laws. In the next chapter, we're going to be solving equations both with logarithms and exponents.